In this short video, we're going to discuss how to get an interference pattern with light. We've seen that you can get an interference pattern with sound and water waves, where you can have two sources, and then that will create, in a two-dimensional pattern, that will create lines where there's always destructive interference and lines where there's constructive interference. We can do the same thing but with light, but the question is how, and how does that work? Alright, so let's imagine we have a laser shining on two slits on a piece of paper. Now the question is what do you think you would see on the opposite end of the wall? Before we can answer what will happen with two slits, we should probably look first at what will happen if you shine light through a single slit. Now, in order to know what will happen, we have to remember about the phenomena known as diffraction. Diffraction is the phenomena that when waves pass by an object or go through a slit or an opening or run into an object in any way, shape, or form, it has a tendency to bend around that object. So normally we would think the waves might be just truncated and just a little bit might go through, straight through, but instead a wave, and this is true with all waves, will diffract. The higher the frequency, the less it diffracts. The lower the frequency, the more it'll spread out. Light has a very high frequency as compared to other things such as sound waves, and so light has a tendency to not bend as much, but it still will spread out. Okay, so let's now take a look then at what oftentimes students will think. They'll say, hey, look, if you shine a laser or light through two slits, you should see two bright spots as light goes through both slits, right? So light will travel and go through and it'll truncate and go to these two spots. But this isn't so. Remember, light diffracts, right? So light from this one will diffract and spread out, as shown by the red waves, and light will hit this slit and diffract and spread out as well. Now this is creating an interference pattern just like we have seen in the past, where when crests meet troughs is a node, or in other words a place of a line of destructive interference, and where crests meet crests and troughs meet troughs, it's constructive interference. So wherever there's constructive interference, on the wall will be a bright spot, because it'll be the two lights will be building and the amplitude will get larger and therefore be brighter. Where there's destructive interference, it'll be a dark spot. And so we'll see a pattern of light spot, dark spot, dark spot, etc. Maybe not this cut and dry, but that's the general idea. This is known as a diffraction pattern. So this is a picture of an actual diffraction pattern through two slits. A laser was shined through two slits, and you can see there are places where it's bright and places where it's dark. Right here is a kind of a dark spot. It's not very visible. Here's a very visible dark spot. But there's light spots and dark spots, and this is created by shining a laser through only two slits. So the thing to take away from this is that whenever you see a problem where there's light shining through two slits, you're going to treat it just like as if you had two sources, like sound sources or two water wave sources, because there's going to be an interference pattern just the same as with the other ones. And it comes from diffraction, not from the fact that the sources themselves are curved. Oftentimes we call these patterns diffraction patterns, but they're the same thing as an interference pattern. It's just caused by this diffraction through slits. And the same equation is used, n lambda equals d sine theta, to calculate locations of constructive and destructive interference, where whole numbers for n give you constructive interference and half numbers give you destructive interference. The only difference, which is barely a difference at all, is that d, where d used to be the source separation, now d will be the slit separation, since that will be our two sources. Like I said, n lambda equals d sine theta is still the equation we're going to use. However, you need to know that there's certain conditions under which this equation really works, under which we can actually get an interference pattern that follows this equation. And so we should know the limitations of this equation. First of all, the points that you're looking at have to be far away. Remember, we derived this equation, but that was assuming that the point we're looking at is far away from the sources. Now what that means is that the distance is far away relative to the source separation. So in the case of light, whatever you're shining that light on, whatever screen or whatever that interference pattern is appearing on, is significantly farther than the distance between the two slits, which is pretty much always true in any problem we'll ever look at. However, there's also requirements for an interference pattern, period. And we really need to know these. These often appear on IB tests in the form of essay questions. So let's review some of those requirements for any kind of interference pattern, whether it be light, sound, or water waves, or whatever. Okay, first of all, those two sources need to be coherent. And this is a really important word that you write down in your notes, coherent, and you remember this term because it'll pop up on a test. Sources need to be coherent. What does that mean? That means that the phase shift between the two sources is always constant. Or if we could put that in other words, that would mean, for example, if I had two speakers, right, and they were in phase, that would mean whenever one speaker creates a compression of a wave, the other speaker also creates a compression as well. And so the two are wiggling together and are in phase. Out of phase would be whenever one speaker creates a compression, the other one creates rarefaction and is going, one speaker cone is going back, the other one is going forward. And they, as long as they stay out of sync, perfectly out of phase, the phase shift difference will always be constant. And that's what we want. We want that phase difference to always be the same. So if they start off, the two speakers start off in phase, as long as they remain in phase, then it's coherent. If they start off out of phase, as long as they remain out of phase, it stays coherent. The problem is when you have, specifically with sound waves, if they're two different frequencies, at first they will be in phase, and then they'll get out of phase, and then they'll get back in phase, and then they'll get out of phase. This is one of the ways in which this means that they are non-coherent, because the phase difference is always changing. The easiest way, usually with most waves, to get a coherent wave is to just have the same frequency. Light, however, is a little bit trickier. Another requirement, and one that we often don't think about, is that the source separation needs to be at least a half a wavelength. Remember, this is because the bigger the source separation, the more interference lines you're going to get, constructive or destructive. And to really get your first destructive interference line, you at least need a half a wavelength difference, right? So bare minimum, a half a wavelength difference of source separation. Okay, so here are a bunch of random examples for you to look at and to see if you can tell if these situations would actually produce an interference pattern. That is to say, locations where there's always constructive interference, and locations where there's always destructive interference. The main thing is to look at whether the waves are coherent or not. That's the main thing. So, for example, two water bugs are jumping up and down on the water at different rates. Would that be create an interference pattern? Hopefully you would think no, because if they're at different rates, the frequencies are different, and therefore the phase difference will change, and they are non-coherent. Two speakers are playing heavy metal music. Would that create an interference pattern? Hopefully you would also think no, because they're playing all kinds of different frequencies, and so again, they are not coherent. Two speakers are out of phase, but are playing the exact same pitch. This will create an interference pattern. Even though they're out of phase, they will, as long as they stay out of phase, and they will, since it's the same frequency, because it's the same pitch, then it will create an interference pattern. Now, granted, because they're out of phase, all the places that we normally think are constructive are now destructive, and vice versa, because our rules of whole numbers, path length difference, whole number of wavelengths of path length difference gives you constructive interference is based off of the idea that their two sources are in phase together. But either way, at least it will create an interference pattern. Two radio antennas emitting the same single frequency of radio waves. Now, normally we'd think, yeah, this is going to be or create interference pattern. But it's possible that the two radio antennas can still emit two exact same frequencies and not be coherent. And we're going to talk about how on another video. And we're going to, in order to know why, it has more to do with the phenomena of how electromagnetic waves, like radio waves and light waves, are created. But for the most part, I would think, probably this would most likely be coherent, but it's just tricky with electromagnetic waves, and the truthful answer is it may not. 4 randomly spaced antennas emitting the same single frequency radio waves. If they're randomly spaced, this definitely will not create a interference pattern. 2 lamps emitting white light. Well, white light is made up of all the different frequencies of color, so it definitely will not create an interference pattern, or at least not a clear one of white light. It perhaps could possibly make an interference pattern for the blue and the white, or blue and the red and the yellow, and they might be different interference patterns, but it wouldn't be clear. However, lamps never emit coherent light, which we're going to talk about later, so this most definitely would not create an interference pattern. 2 speakers both playing the same 2 pitches simultaneously. This should create a coherent, these are coherent sources and should create an interference pattern. So how can we make light create an interference pattern? You can see that on all the other examples we had issues with creating it. And the main thing is it has to be coherent and it has to be monochromatic. That means that it's one color, right? That's because if you want one color, if you have one color, you have one frequency, and they have to be coherent. Just being one frequency or the same frequency does not guarantee coherence with light waves or other electromagnetic waves. So exactly how do we get coherent and monochromatic light? We're going to talk about that in our next video about the phenomena of waves, because we first need to learn about some factors about waves first.